So to go from a function to the inverse of that function, do I either one of these? The midterm review? I might have those on me. Wonderful. There you go. One of them. Cool. Who else needs a copy of the rules in the car? I'll grab it from your room. Anyone else? There you go. Awesome. So, let's talk about inverse functions. So the things to remember about inverse functions. So what does the inverse function mean? If you say y is the output that corresponds to an input value of x into the function f, inverse functions will swap those two rules. Y equals f of x means that x is equal to f inverse of y. So that's like the input and output values have been swapped. So that means on a graph, the x and y values will swap because x is our input values, y is our output values. To algebraically find a formula for the inverse function, we'll swap the roles of inputs and outputs, and then solve for the thing that's supposed to be the output. So there's a 2-minute summary of what happened last time. Let's see all of those things in practice for one particular function. Here is a function, f of x equals x minus 1 divided by x minus 2. If you wanted to find the inverse to this function, what equation do you need to solve? Yeah. Equals x. Nice. So, I think here's how I want today to begin. Collaborate with each other if appropriate. Tell me, what is the inverse to that function? While that happens, I'm going to take attendance. So that's, which is now moving again. Okay. So, how do people feel about this? Any folks arrive at a conclusion? Any folks just want more time to get their conclusion before we come back? Cool. Let's talk through what partial progress people made then. Or maybe I'll give one last call. Anyone settle down to an actual answer? Okay, then let's talk through it. So there's an equation you would like to solve for y. It's annoying that there are like some y's in the denominator. Where like you can't get it. How can you get those y's to not be in the denominator? Yeah, for us to multiply that denominator with y. So multiply both sides by y minus 2. You'd wind up with y minus 2 times x equals y minus 1. All right, so now there are y's on both sides of the fraction. That's a little annoying, but not that bad. It's annoying that there's like a y inside of those parentheses that has the x multiplied by it. So how do you like eliminate those parentheses? Yeah. Let's distribute the x to it. That'll be yx minus 2x equals y minus 1. All right, so now I guess I'm annoyed that there are y's on both sides. Can we arrange that all of those y's are on the same side? Yeah, what would you want to do that? Let's subtract y from both sides. That will move this y to the other side. And you know what? I would like this 2x because it doesn't have any y's in it to move to the other side. So let's do that to both sides. So doing that, I think that you wind up with yx minus y equals 2x minus 1. That done correctly? Nice. Okay, cool. What next? All the y's are on the same side now. That's nice. Factor out y. All the y's are on the same side, and all of the y's are only like degree 1. So that means I can pull a y out of everything on the right-hand side, and I'll see y times some stuff. Y times x minus 1 equals 2x minus 1. Okie dokie. What next? Yeah, divide by whatever it is that's next to that y. Since that's now the only y in sight, that's a good thing to do, because then it'll just be y on its own. Divide both sides by x minus 1. Y equals 2x minus 1 all over x minus 1. So it sure looks like f inverse of x is 2x minus 1 over x minus 1. And let's see, I know that I asked y'all last time if you ever go through and use the QR codes that are in the packet, use it now. But at the other end of that particular QR code are some relevant graphs. So let's look at those relevant graphs. So here we see, well, right, I can't actually use the QR code because this machine doesn't know how to read a QR code as far as I know. Let's graph some things. Let's look at this function, x minus 1 over x minus 2. And there is the graph of y equals f of x. I know what the inverse function should do. It should swap the role of x and y, which happily Desmos is perfectly happy to graph a function of the form x equals f of y. So the green graph, whatever it is, must be the graph of the inverse function. We've just found a formula for the graph of the inverse function. Let's see if it agrees with that green thing by graphing it. 2x minus 1 divided by x minus 1. Purple and green graphs seem to line up pretty good. All right, I'm reasonably confident that this is correctly done, the inverse function to this original function. All right, so what are we going to do with the rest of this section? We're going to say some things about domains and ranges. We are going to use those things about domains and ranges to see if our inverse function is correct. And then we'll wax a little bit technical and give the full-blown correct definition of the inverse function and check that this function above is actually the inverse to the function we want. So let's go ahead and get started. Let's think about domains and ranges. And let's start by just asking these questions in order. If I give you a function f of x, how do you read off the domain of that function from the graph? Yeah. Yeah, it's all the x values that correspond to some y value on the graph. Maybe I'll write that as a slight shorthand. It's just all the x values you see on the graph. All of the x values on the graph. So that's how you get the domain of a function. How do you get domains of a function?
Yeah. All of the y values in the graph.
Yeah. Exact same as above, just replace x with y. So here's what I'm going to be interested in writing it down in this theorem statement in the middle of the page. What's the domain and range of an inverse function? And let's think about it in terms of this. How does the graph of the inverse function compare with the graph of the original function? Yeah. Reflected over y equals x. And I'm going to, right, there are two different ways of saying this. Reflect over y equals x. What does that do to xy coordinates? Yeah. Yes. Yeah, so I'm going to write what's going to go in the theorem statement. The domain of the inverse function is the same as the range of the original. Absolutely. The range of the inverse function is the same as the domain of f. And the reason that that's true is, what is the range of the inverse function? It's all of the y values on the graph of the inverse function. But the inverse function has the exact same graph as the original function, just with x and y values swapped. So if you want the range of the inverse function, that means you want all the y values on the... Nope, you want the domain of the original of the inverse. That means you want all the x values on the graph of the inverse. That's the same as all of the y values on the original graph. That's the range of the original function. And the same thing goes the opposite way too. So domains and ranges swap for inverse functions, and the reason that they do that is because the x and y values on the graph swap. Feel pretty good? Nice. So let's check that against this computation we just did. For this function, we got f inverse of x to be 2x minus 1 over x minus 1. So let's compute domain and range of the function and the inverse and see if they actually line up correctly. X minus 1 over x minus 2. What's the only thing that's not in the domain of that function? Yeah. 2. Why 2? Yeah. To find the domain of an inverse function, ask when do you divide by 0? Those are the things not in the domain. If you look at the graph of that function, you'll see that the only thing not in the range is this horizontal asymptote. This function never crosses its horizontal asymptote. Some do, this one doesn't. So the horizontal asymptote is the only thing not in the range. Where's the horizontal asymptote of that function? 1. Why 1?
Since the coefficients are the same, you divide it, and it's just 1 divided by 1.
Awesome. It's degree 1 over degree 1. Compare leading coefficients. So the only thing not in the range is y equals 1. Let's see if the exact opposite happens for the alleged inverse function. What's the only thing not in the domain of this function? Yeah, but say it louder. 1, right? You ask, when do you divide by 0? At x equals 1. Oh, cool. Those two things line up correctly. The hole in the range of the original function is the same as the hole in the domain of the inverse function. The only thing not in the range, again, will be the horizontal asymptote. Where does this function have a horizontal asymptote? Yeah. Y equals 2. And again, we see those two things line up correctly. So if you want, so that again should help reinforce that this computation of inverse function is actually correct. But let's close with this one last technical thing, which will be the full-blown correct definition of what the inverse function is. And we'll check that the function we found actually satisfies it. So here's what the inverse function should do. If I give you a function f of x, then the inverse, f inverse of x, is the unique function which satisfies two equations. If you compose the inverse of a function with the original function, you should just get the input back. So f inverse of f of x is equal to x, and f of f inverse of x should always be equal to x. So if we actually believe that this function's inverse is the thing we computed, we should be able to check that by doing some function composition. Let's do exactly that. So let's check that the inverse to this is what we computed it to be. Oh, yeah. And if I remember right, we got 2x minus 1 over x minus 1 as the inverse to this function. My short-term memory is very bad. 2x minus 1 over x minus 1. Yes, okay. Let's check that it's actually the inverse function by using the definition. So to check that this is actually the inverse function, here are the things we need to compute. We need to compute f of f inverse of x. That better be equal to x. And we'll need to form that f inverse of f of x is also equal to x. Those are the two things we need to check. And I think in the time right now, we have plenty of time to check at least one of them. In fact, exactly one. Let's pick one of these two and check that one. Which one should we do, first or second? First? Second. All right, this is a way better turnout than that same poll had an hour ago. There was like 2 fingers went up for one of the columns and none for the other. I like that it was a good turnout and also one-sided. So, in order to check this, let's compute that and see if it works out to be just x. So here's the upshot. We need to compute f of f inverse of x. I know for a fact that, well, I'm confident because I'm confident that this computation was done correctly, that the result should just be x. So I know what the result should be, but I have to get there. So this is like a function composition problem. I have a general strategy for function composition. I'll color code a little bit. Lighter blue and darker blue. That didn't show up at all. Lighter blue and pink. So, do I have a formula for what f of x is? If I want f of f inverse of x, I need to replace all the x's in f of x with f inverse of x. So that'll be 2 times f inverse of x minus 1. Nope. F inverse of x minus 1. I need to use this formula. All over f inverse of x minus 2. Do I have a formula for f inverse of x right now? Let's use that. This should be the exact same as 2x minus 1 over x minus 1 minus 1 all over 2x minus 1 over x minus 1 minus 2. So there's some complicated looking formula. I know for a fact that it should simplify down to just x. And the fact that it looks complicated is actually helpful. That tells me that there should be lots of space to simplify. And in looking at this, we need to simplify. We know that we should get down to just x eventually. What seems like a thing, well, how would you want to simplify this? Yeah.
Integrate -1, -2 into the respective fractions.
Yeah, so I see a fraction minus a number over a fraction minus a number. If it were just fraction over fraction, you would multiply by the reciprocal. So that's cool. Let's get it into the state of being just a fraction over a fraction. Let's do it by getting some common denominators, by doing exactly what you said. So maybe you would do what I'm about to do in 2 steps, and maybe you would do it in 1, but I'll do it in 2 steps. I'll write that 1 as something with an x minus 1 in the denominator. So I guess that 1 becomes x minus 1 over x minus 1. And I think I can do away with my color coding now. 2x minus 1 over x minus 1 minus x minus 1 over x minus 1 all over. Same thing in the denominator? If anything, I think it's more important in the denominator because that's where I'm going to, like, that's the thing that I need to be able to take the reciprocal of. So 2x minus 1 over x minus 1 minus 2x minus 1 all over x minus 1. Fair enough? And, like, what I'm about to do is maybe, like, the thing that you would have combined into a single step. So let's now focus just in the numerator and then just in the denominator and see what fractions we get. All right, you look just in the numerator. What can you do now that you have a common denominator? Yeah, say it louder there. I heard someone whisper something that was good. Or maybe I imagined it. What seems like something good? We will be able to, as soon as in the bottom, we just see a single fraction. So let's get a single fraction down there, and then we can play that here. So I guess that means I need to take advantage of common denominator to just subtract the numerators. So let's do that. So in the numerator, I'll see a bunch of stuff over x minus 1, namely 2x minus 1 minus x minus minus 1 plus 1. So there's some distributing that minus sign. Put some parentheses around it so I can tell where the big fraction bar actually goes. In the denominator, 2x minus 1 all over x minus 1 minus 2x minus 2 times minus 1 is plus 2. Feel pretty good so far? All right, do I now see a fraction divided by a fraction? So I think it seems totally reasonable to multiply by the reciprocal, but maybe before we do that, we should, like, combine some common terms or cancel some things that cancel. What cancels? Yeah, so I see a plus 1 and a minus 1, those will cancel. I also see 2x minus x. So what does that whole numerator and the numerator become? Just x. So I'll end up with x over x minus 1. I haven't done anything with the x minus 1 yet. All over. What does the thing in the bottom become? I go 1 over x minus 1. Does that agree? Nice. Oh, yeah, sorry. Thank you. Cool. Now can we multiply by the reciprocal? In fact, how many people at this point would just do one more bit of canceling instead of multiplying by the reciprocal? Cool. That'll work too. I'll multiply by the reciprocal, and then we'll see the thing that cancels. All right, so that becomes the same as x over x minus 1 times x minus 1 over x. Does anything cancel? X minus 1's cancel. If you divide by x minus 1 and then multiply by x minus 1, those two undo each other. You wind up with just x. Is that what we wanted to get? So this conforms that f of f inverse of x equals x, which is the thing that we needed. There's still one more. Yeah.
I was wondering, like, with the meeting, like, what you're doing there, could you not have, like, multiplied the numerator by x minus 1 and multiplied the denominator by x minus 1?
Absolutely. So let's see what would happen if you did. So here is a sneakier thing. No, I guess that would go here. That you could do, which requires like a clever step, but if you do it, works out to be faster. So I'll write it down. So you could rewrite this as 2x minus 1 over x minus 1 minus 1 times x minus 1 all over 2x minus 1 over x minus 1 minus 2 times x minus 1. Now you can always multiply and divide by a single number without changing the fraction. And, well, let's not actually do it, but let's imagine that you distributed that x minus 1 through on the numerator and denominator. Would that make the sub-fractions go away? Which would be nice. So there's a strategy. The reason I didn't do that is because it didn't seem like the way the flow of the discussion was going. That'll be a way that'll be a few steps shorter if you do it. And one of the points here is, just because I do something using one sequence of algebraic steps doesn't mean that's the only sequence of algebraic steps that does a thing. There are lots of different ways to do a thing. There's more than one way to shake a stick. Is that the saying? There's precisely one way to shake a stick. You just shake the stick. You know what I mean. Cool. Any questions right now other than what was that idiom? Nice. So, let's start in on the new topic I want to start in on today, namely exponential functions. And one more thing, sorry. So, let's talk about exponential functions by introducing them with a simple example. Let's talk about the trouble with triples. So, let's suppose that you start with a tribble. You have a tribble, it's a nice, cuddly, fluffy animal. It has the property that after 1 hour, it will split into 2 triples. So, after 1 hour, you now have 2 triples. If you wait another hour, those 2 triples will again split into 2 triples each. So how many triples will you have at 2 hours? 4. Twice as many as you had before. At time equals 3 hours, how many triples will you have? Well, each of those 4 triples will split again. 8. After another hour, each of those 8 triples will split again. At time equals 5 hours? Let's jump up by a whole lot. After 49 hours, how many triples will you have? Yeah, so the fancy way of saying it is 2 to the power of 49. Let's introduce some notation. After any amount of time, after n hours, the number of triples you have, well, at time equals 1, you had 2 of them. To get that thing at 2 hours, you have 2 times 2, 2 times 2 times 2, 2 times 2 times 2 times 2. Just 2 multiplied by itself the right number of times. To get the number of triples at n hours, you just take 2 and you multiply it by itself the correct number of times. And the fancy notation for that is 2 to the power n, or if you're looking for how to type it into most calculator machines, 2 apostrophe n. Or if you find yourself using something like, let's see, I believe Python, Java, Perl, and C all follow this notation. 2 * n if you're using one of those languages. That doesn't matter for the sake of this class. Nice. So, if you want the number of triples after 49 hours, it will be 2 raised to the power of 49. And maybe I'll encourage for this computation the use of a calculator. What is 2 to the power of 49, approximately? Yeah.
5.63 times 10 to the 14th.
5.6 times 10 to the 14th power. And let's just think about what that means. So that'll be a 15-digit number whose top 2 digits are 5 and 6. So 5, 6, and then 14 more zeros after that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So about that many. So kind of a lot, right? So let's ask this. So here's the takeaway here. It's a big number. Exponentials tend to get big pretty quickly. After 6 hours and 20 minutes, how many triples will we have? And that's, like, this is like a discussion. What do you think? I can recall for 64. Why 64?
They don't split so they're 7 and 20 is 63rd plus 7.
2 to the 6th, since they split seemingly on the hour. So there's one way of interpreting this question, Sean. Do you know for sure that, like, does the problem make it totally explicit that they split, like, exactly after the hour? So, because you know, maybe you interpret it more like, on average, a triple takes an hour, because you can type to split. In that case, maybe just taking 2 to the 6th doesn't seem quite reasonable. Which is why I wanted this to be like a discussion. This would be an answer that we get. A few other hands. I think you will want.
It doesn't necessarily split every hour. It would be like 63rd, right?
2 to the 6th plus a third. That seems sensible. Is that what you two were going to also add? Yeah. Or maybe you would say like 6.33, but this way I'm still exact. If we wanted to be approximate, let's be approximate. And all right, we could write 6 and a third as 19 thirds if we wanted to. I don't think I will. I think this is good enough for me. This apparently is approximately like 80, whereas this was 64 on the nose. So maybe you'll notice something weird. This predicts like a non-integer number of triples.
You have a number of triples.
No. So that is in some sense built into this. They take approximately an hour to split on average. So maybe you can't predict this number exactly, but I think the number you would predict as about the number of triples you should expect is about 80. And this is something that's true whenever you use exponential models to predict populations. You'll wind up with lots of times when it'll predict a non-integer number of individuals. And you should interpret that as being, well, this model is approximate as opposed to exact. And that's just the way of things. You're using a continuous thing to model a discrete thing. You can only have a whole number of individuals in the population, but this function is continuous. It's perfectly happy to take any input and give you any output. So that's just something to worry about whenever you're using exponentials to model. Otherwise, people feel good right now? Yeah. So, let's talk about exponential functions in general. So, let's fix any base, b. I know what b to the power n should mean when n is any, like, counting number. It just means b times b times b that number of times. B to the n means b times b times b dot 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 times b. How many times? N times. as a consequence, let's just go back over here. What should 2 to the power 3 mean? 2 times 2 times 2. And what is 2 times 2 times 2? Negative powers. So let's think about negative powers like this. So if you raise 2 to a positive power, that means you like multiply by 2 that many times. Raising to a negative power should be like the opposite. What's the opposite of multiplying by 2 a bunch of times? Dividing by 2 a bunch of times. Or b for any b. If you have b to the power of negative n, that should be the same thing as dividing by b a bunch of times. Fair enough. And there are a few other ways we could write this. That's the same as multiplying by b a bunch of times in the denominator, right? Oh, but notice that's also the same as 1 over b to the power of n. So if you want to raise something to a negative power, on that base instead to its reciprocal and then raise to the positive that power. Or, if you like, is the same as 1 over b to the n. So, let's see what that means. Using this step, what should 4 to the power of negative 3 mean? Yeah. 1/4 to the 3rd power, which I guess would be the same as 1/4 times 1/4 times 1/4. And what is that equal to? You're a 1 over 64? Cool. I think someone right before that said the right thing too, but my ear was itchy and my itch was noisy. That doesn't matter to you. I just wanted to explain why I think I missed something. B to the power 0. So let's think of it this way. So b to the n should be like b times b times b that many times. So b to the power 0 should be like what you get if you don't multiply by b at all. So what should that be? I got a 1 and I got a 0. Both of those are like sensible. Let me tell you why I'm going to prefer 1 instead. So b to the 1, that should just be b, right? B times itself once is b. So that should be the same as like no b is written in the row, and then multiplied by b once. That seems reasonable, I hope. If you multiply by b by itself no times, then multiply by b once, you should get multiplying by b once. So what would you want to put there for b to the 0 to make that true? 1. So b to the 0, I will assign to be 1. Provided that b itself isn't 0. 0 to the 0th power is something that you need to, like, be weirded out by. It doesn't really make sense. Rational power is b to the power p over q. So to think about that, let's think about what, like, 2 to the 1/2 should mean. So 2 to the 1/2 should be like, raising something to the 1/2 should be like the opposite of raising it to the second power. So the opposite of squaring. What's the opposite of squaring? Square root. So 2 to the 1/2 should be like root 2. 2 to the 1/3, that should be like the opposite of cubing. What's the opposite of cubing? In general, b to the 1 over q is another way of saying the qth root of b. I don't know. How many people have noticed that your calculator has like a square root button, but maybe doesn't have a cube root button or a fourth root button? Yeah, here's how you can do it. Raise things to fractional powers instead. Your calculator will be perfectly happy to do this. If you want b to the power p over q, for any fraction p over q, well, you can think of that by taking the qth root of b and then raising it to the pth power. provided that b is a positive number. Negative numbers in the base can get dicey because, like, the square root of a negative gets dicey. In fact, it gets dicey even if you think in terms of exponentials. You need to, like, worry a lot about exactly what it should be. Folks feel pretty good? Nice. So, let's use those ideas to, like, do some more computations. If you want an 8 to the power of 5 over 3, let's think of it this way. I want to start with 8. Because of the over 3, I want to take the cube root of 8, and then I want to raise that to the 5th power. So let's work that out. What's the cube root of 8? 2. So this should be the same thing as 2 to the 5th. What's 2 to the 5th? Nice. Folks feel pretty good? If you want something like 10 to the 5th by this same idea, just to see that this idea sometimes doesn't work so great, you should start with 10, then take the 5th root, and then cube it. Do you know what 5th root for 10? No, I guess it should be like a little bit bigger than 1, but probably not much bigger than 1. This 2 to the 5th is already pretty big. So if you want to compute something like this, in this class we won't develop good computational tools for that. Instead, I'll resort to a machine to compute things like 10 to the power 3 over 5. Is about 3.98. Maybe I'll pull the hood back a little bit and say what the computer is actually doing. So the computer isn't trying to actually take like a 5th root and then cube the result. That would be too hard. One of the tools that you'll build when you take, in second semester calculus, are called Taylor polynomials. So the philosophy of calculus says that basically any function can be estimated by polynomials. These polynomials are called the Taylor polynomials. You can find a polynomial that estimates 10 to the power of x. And once you have that polynomial, just plug in x equals 3/5 and see what you get. So that's what the calculator does. I'm not going to explore those in any more detail than that right now. That'll happen when you take calculus. How many people are taking at least first semester calculus next term? How many people are planning on going on to second semester calculus? Okay, that's a shame, because that's when Taylor polynomials really happen. Nice. You can walk further than that. You could understand 10 to the power pi to the power 10.44, because 10.44 is another like rational number. It's 1044 divided by 100. So you can take the 100th root of pi and then raise it to 1044. Does that seem like it would be easy to do in practice? No, I wouldn't do that in practice. This is another time when you would use the techniques that the calculator uses. And same thing with things like e to the square root of 2. You could compute those. There are really good tools for computing e to the x, because e to the x is, well, defined so it has nice calculus properties. Compute those using a machine. Folks feel good right now? Let's think about graphs of exponentials. I think we have enough time to do this one last thing. I have 4 minutes. Let's sketch the graph of 2 to the x. And let's do it by plotting some points. Yeah. Oh yeah, I don't need that right now. What's 2 to the power 0? Anything to the power 0 is 1. So that means x equals 0, y equals 1 should be on the graph. What's 2 to the power 1? 2. What's 2 to the power 2? What's 2 to the power 3? What's 2 to the, well, okay, 4, 8. What's 2 to the power 4? 16 and 8, 9, 10, 11, 12, 13, 14, 15, 16. So there are some positive powers of 2. Do you think I could fit 2 to the 5th on this graph? It'd probably be like there-ish. So let's stop there going to the right. Let's think about negative powers. What's 2 to the negative 1? 1 over 2. Maybe 0.5 if you like decimals. What's 2 to the power negative 2? 1/4. Half as big as that. What's 2 to the power negative 3? Nice. So let's draw those remaining dots. And if you want to get a sense for what the graph looks like, let's try to interpolate between. So there's the graph of 2 to the x. Maybe to get a quick check. Let's have a computer do the same. Caps lock. So there's the graph of 2 to the x. Does that look about like what we just sketched? Qualitatively. So let's give a quick tour of what's in this packet that we'll do, I guess, on Monday, because there's going to be a review for the midterm, then our midterm day. We'll get the so-called exponential laws, which will let us compute things like multiplication of exponentials, exponentials of exponentials. We'll solve some equations, and then close by thinking about graphs of exponentials in general. Cool. So maybe I'll say these two last things. There was like one of these pop quizzes on Monday. If you missed Monday, you may have just noticed that a 0 was entered into your grade. If you can make it by my office at 1 o'clock today, we can make up that quiz. Otherwise, you can shoot me an email, tell me why you didn't show up to class, and we'll have you take the quiz. I don't have a list of who missed it. You know if you missed it. Yeah.
Thank you all.
Yes, see you at 1.